So I don't know if you know much about fast Fourier. I'm not even saying it right. Fast Fourier transforms. Where
yeah. I use Fourier transformation as well.
cool. And would you be using that in terms from the point of view of like quantum mechanics or?
No. I actually, my research is nuclear energy related. It's corrosion.
Sorry, what's the word?
Corrosion. I research the material and the water chemistry, the interaction. So
okay, so in water, you erode like corrosion and erosion, or corrosion more.
Yeah. I use electrochemical impedance spectroscopy, electrochemical noise, like this.
Oh yeah, but what do you mean electrochemical noise from like, and what source?
Corrosion process, yeah.
Oh right, yeah, actually that's interesting. You should talk to Rajan then, because he spent, I think, the first 20 years or more of his research studying that side of things, but with a mind to creating visual simulations of them, so computer simulations, and it was all around applying finite field simulations to corrosion, chemical corrosion, which is a subject I'd never heard of before, but he's mad into finite fields. Yeah, you know what I'm talking about, the finite element, sorry.
Finite element analysis, yeah.
That's the word, sorry,
yeah.
So he's mad into that, and he did a lot of stuff on corrosion, he was telling me, and he wants to bring all of that into his current research on, he has this idea called a PDP circuit. I've forgotten what PDP stands for, but it's like the name of three physicists, so it's like Pauli, Dirac, and the third one escapes me, but it's not too important. Yeah, so he's thinking about like it's some sort of assembly matrix that rotates and then it puts different things. So it would be like loads of them, I guess, in a matrix, and then like each node, it represents one of these PDP circuits and then a link. It's pretty out there. I don't get it, but he knows what he's talking about, I'm sure, and eventually I'm sure it'll click. But yeah, I have a certain kind of non-relativistic quantum mechanical simulations that I do. Like I like to work just within quantum mechanics and like keep relativity as sort of separate as I can for now.
Okay.
So the idea is I start with very simple assumptions and keep building up until so if I encounter something that's like, you have to include general relativity in this, then I will obviously. But so far I've been able to work without it quite well. So that's kind of the track I'm going with at the moment. So for instance, I'd be able to model spin 2, where you have spin 1.
Hi.
Hey Raj, are you with us now? Great. How are you keeping? Sort of with us. Okay, not to worry. It's probably like 12 in the afternoon where you are, Rajan. So I don't know. It's a different story where we are.
Can you hear me?
Yeah, I can hear you now. Yeah.
Oh, okay. I had some problem with the internet thing. So now I am able to connect. I mean, the normal internet, I don't know why it was not working. It should have been.
Yeah.
So sorry, I missed. You were mentioning about a paper. After that, I lost connection.
No problem. Yeah, I think I was just explaining what the kind of background is of the meetings and what their purpose is. I didn't even really get into, so I think I pretty much covered most of that. And then Wenzhong was explaining what his sort of, you say, field or discipline is, and I noticed that it was quite similar to work you'd done in the past on corrosion, chemical corrosion, and so we were just talking about that, and then I was sort of explaining the PDP circuit as best as I could, and then moving on, and then kind of explaining some of my work, how it relates.
We got so far the Galley proof, so we are just waiting to get that. I think we'll get published then.
Sorry, what is this? The paper?
We are waiting for the Galley proof, I think.
What is that? I don't know what that is.
It's before the publication. They send, you know, to see that everything is okay and how it will appear. So then we look at that. I think so. I don't know whether they'll publish before that or they send, you know, online and they send the Galley proof simultaneously. I'm not sure. I think,
but it is all sorted. Like they accepted the paper and great.
Essentially, So just have to wait for that. Hello, Dr. Zhang. Welcome. Are you able to hear?
Yeah.
Okay.
Yeah. Welcome.
Oh well, yeah.
Nice to you know you, but cannot see you.
Yeah, you are. Yeah, actually, I'm trying to switch on. I don't know why it's not switching on.
Yeah, it's great to have you here, Wenzhong. So, are you from China originally, or are you Malaysian?
Yeah,
or?
I'm from China. Yeah.
Cool.
But what is your background?
Yeah, my background is nuclear reactor. You know, mainly is corrosion, materials and corrosion. Yeah.
My original background is corrosion, hydrogen embrittlement, corrosion. That's PhD was in stress corrosion.
Oh.
Yeah, material science. So what kind of corrosion were you doing?
Yeah, quite a lot. When I worked in Beijing, actually I joined several large projects to develop new alloy. So my job is try to help them to evaluate the corrosion, you know, behavior of the materials and the welding joint. But since I moved to UK, I gradually moved to electrochemistry, you know, electrochemical technology to evaluate corrosion for quite a long time. Now, now my project is corrosion fatigue. Actually, it's a kind of.
I did a lot of electrochemistry. I did a model called IPC model. You may see that in a ResearchGate if you are there. I published with the Stanford annual review. I worked with Professor Pickering at Penn State University and Zamanzadeh, Dr. Zamanzadeh, and I had an original model. Now it's considered #2 model for hydrogen embrittlement, hydrogen entry to evaluate absorption, because they couldn't find. There are two things: absorption and adsorption, as you know, in the hydrogen, and you know, the Bockris model, which is the main book in electrochemistry. I mean, he has written a lot of books with Reddy in the quantum electrochemistry. Probably you know that, the Bockris model, but they cannot they cannot differentiate between or discriminate between absorption and absorption. So together only they could figure out. But I found a new model where I can find separately the absorption, and find the value. That has proved people are using quite a lot. We have a lot of citations for that. So that's electrochemistry aspect. But originally I'm always interested in physics. So that's why I start, because there is a connection, and I have put how to apply that metrics. I develop a metrics graphing, how to apply for the equation of motion. And then I came across a lot of the problems that physics has. So are you also working in physics?
Yeah, because for the past few years, my main project is fatigue, behavior of materials and corrosion fatigue. Originally, I tried to understand the mechanism of fatigue. So I tried to use the, you know, a harmonic oscillator model, try to understand the fatigue. But later on, I found that based on this model, actually, I found there problem with, the modern foundation series of physics. So I used my spare time, weekend, holiday. I try to, based on the, simple harmonic oscillating model, try to, develop a new, a radical new foundation theory of physics.
Oh.
Okay.
So I published 4 papers in the Canadian Journal of Pure and Applied Science.
Yeah, I've seen some of those. So
what is your major, what is a, are you developing a new oscillator or?
No, I'm a
oscillator?
senior. I'm a
Helmholtz,
senior.
are you using Helmholtz? I mean, are you using Hamiltonian?
Harmonic, oscillating.
But Hamiltonian operator, are you using the quantum Schrodinger Hamiltonian, the Schrodinger equation?
It's basically a simple spring model,
Oh,
okay.
Simple, okay.
Yeah, and I found, both Einstein's relatives and quantum mechanics, they have some assumptions.
Yes.
Idea, approximations. So I try to develop a new foundation series, try to combine them together and develop a theory can be used in macro systems and macros, and also, the macro and macro system. Yeah, now the 4 paper published is mainly, try to understanding some actual physics observations.
Oh, okay.
But now I'm trying to use this theory, try to to explain some, some thing quantum mechanics can explain.
Oh,
okay. You do talk a lot about Lagrange and the Hamiltonian and how they're not ideal or something to do with they lack a model with friction.
Yeah. I that's what I found. Einstein's, general relativities, actually there's no friction. They ignore the friction of the vacuum. So
interesting.
Yeah. I add the friction in. I can get some very good, explanation of lots of the, the astronomic observations without assumption. Now the cosmologists, the Big Bang standard, Big Bang cosmologists, they build upon lots of assumptions, or So if I use a damped, oscillating model, add friction into the vacuum, you actually their evidence shows their friction in vacuum. Solid, some published paper already verified there is friction in vacuum. So based on the damped oscillating model, so I can derive for example, the Hubble constant and the redshift relationship, and also the modified Tully-Fisher law, the modified Newtonian dynamics, and can calculate the, the the microwave background radiation temperature and also the spectrum. So it's all quantitatively, you know, it's
what? Sorry.
Quantitatively.
Quantitatively?
Yeah. It's not you know only a you know estimation. It's you can calculate quantitatively. Yeah.
Yeah, I get you. Okay, so it's interesting. Yeah, friction in a vacuum, it's an interesting concept.
Yeah.
I mean, it sounds strange, but it must be so. Like, it seems interesting, but it must be absolutely minor. Is it like tiny amount?
Yeah, extremely, you know, tiny. But within our solar system, you can ignore it. That's no problem. But if you can consider the distance in our, you know, larger than our solar system, if you ignore it, you have a problem.
Okay, so you're talking about for like really big things.
Yeah.
Vacuum on a quantitative scale suddenly becomes a drag on things.
Yeah.
Interesting.
Right. In our Milky Way.
This doesn't help with dark matter or anything like that, does it?
No, we do not need the dark matter. We do not need the dark energy. If you only need to introduce the friction to the vacuum, then you solve all the problem.
Oh, interesting. Can you give me because this is new to me? Can you explain like simply how that works?
Okay. Let's see. First, I agree for the photons. Let's see the photons. For the photons, do you agree the angular momentum of the photons is a constant, do not change with time?
I would say yeah.
Yeah, the Planck constant. Actually, Planck the reduced Planck constant, the H bar.
Yes.
It's constant. That is the angular momentum of the photon. Yeah.
I had no idea.
Yeah. Yeah.
What it was like.
Yeah, it does change with time.
Okay, yeah, because the 2 pi or is the Oh, of course, right. Okay, that makes sense. Yeah.
Yeah. Do you agree? You know, in the vacuum, in the free space, the speed of light is a constant. Do not change with time.
Yeah, of course. I mean, that is the one of the basic fundamentals of general relativity, special relativity. So, I mean, I would agree with that from the tenets of relativity. Of course.
I can see me now, right?
No, yeah, we can see you now.
Oh, okay, good.
No, I can't. No, your video isn't on, Raja. Like, we can just see your name or G.
Oh, the video is not there.
Can you see the video, Wenzhong?
I cannot see video. I can see Raja now. Yeah.
But can you see Rajan's like face, his video?
Yeah, I can see.
Okay, I can't see it, but
I can see. Yeah, very clearly.
Okay.
Oh, okay, good. Thank you.
Yeah. It's not coming through.
Yeah, there was an internet problem, so I had to connect through another system.
Maybe that's
kind of weird that I don't know. Sometimes they accept the wireless. I have an old laptop, but it was working fine. I am using it all this time. And today I try to, I kind of trying to catch up because I have other things to do. So I switched on and the internet will not come here. So I switched on my computer but the computer does not have mic or camera. So I can hear you, but I can only chat with you. Then I somehow connected through another code temporarily now. I had to fix this, but Maybe I had to use this. So now I am finally able to connect. So all these crazy things are going on. But
Rajan, could you do us a favor? Maybe turn on and off your camera.
okay.
Just to see if that helps. But yes.
Perfect. Can see. Yeah, it's some switch problem. You can see everything now. Okay.
Yeah.
Good. So so our model very similar, but we started from point field. It's called Markoulakis. Emmanuel is from Greece. So I myself here started working, and he has a new observation of something called magneton. It's like a monopole that you can see at the room at the mesoscopic level at our. So he has a new technique called ferro lens, and we published a paper called Theory of Superluminous recently, and there we talk about point. See, there are two. It's called Helmholtz decomposition of field. Okay, there are two types of fields: gradient field or irrotational field, and rotational field, which is vortex field. So if you use that matrix, we use that 2x2 matrix, we can come up with a whole set of partial differential equation that describes the field, the quantum field, eigenfield, and also eigenfunction, everything. And I use that and develop a problem. There's another paper called problem solving. We did that, and then I gauged. You can gauge it to electromagnetic. That's what we sent a paper. And there's a paper in between, couple of papers, which shows how to gauge it, the Coulomb gauge and Hilbert and the Higgs type of field. And now we change to gauge that we use a new circuitry. We found a new novel circuitry at the subquantum level. Probably like few orders of Planck magnitude. It consists of both monopoles and particles, electron positrons, north monopole, south monopole, everything together. They act like a clock. So that's what we submitted, and recently we got there are a lot of revisions we had to do. They said they'll accept a lot of conditions, so we had to do a lot of overhauling the whole paper, and finally we did that together. Myself, Christopher especially, worked together, and we produced a lot of figures, pictures of how the scenarios occur, and we came up with a scenario that's best suitable, and that's going to be quite. And they were quite satisfied, and they wanted to add something about antenna. There was another one there, about FEM, finite element modeling. I don't know whether you have done that, but that's another area. And then the editor wanted some more revisions. So we went through all that. Now they are accepted our paper. So they said they will publish it, but they'll have Galilei proof. So I not heard after that, but I think, probably in a month's time, we hope to, have it online, because in open access. So it should come on online. I think everything is set except Galilei proof. I don't know exactly how they're going to do, but previously they sent, okay, these are the things before we activate the internet, look through and say everything is okay if you want to change. And then once you approve that, they will put it online.
Yeah, Rajan, you said, I thought you said the circuit was like 10 to the, was it
10 to the power minus 26 meters.
Right, so that is a good bit below Planck scale, which is like
Planck scale 10 to the power minus 34.
Okay, so yeah, so that's what I was thinking. So it's bigger than the Planck scale.
Yeah. It's slightly even bigger than the monopole size. I have put in the table. It's 10 to the power minus 30.
Yeah, it's
estimated. Yeah, so it's a little bigger than that because there are more things in there, right?
But you said yes there that it was you were talking about a circuit being 2 orders of Planck scale, which is tiny, yeah?
No, it's like 10 to the power 8 times.
No, just like when you were talking there the last 2 minutes, you mentioned that you found a circuit that was 2 orders of.
No, many orders, many. Sorry.
Oh, sorry. Okay.
Yeah. It's all right. Thank you for clarifying.
Okay, good,
Yeah.
good. Because
Yeah.
I'd need
Yeah,
you to run through the whole thing again if that was the case. I'd be like, what?
Yeah.
Okay,
10
that's
to the
great.
minus 26. It is like 4 orders of magnitude more than a monopole. And we would expect that because it's only not only monopole, but also the particle, positron, electron. So we would express, although they will get compressed.
Well,
you
it's
know,
very interesting, Rajan.
Yeah.
Really interesting research, and I've got a number of questions about the theory, like later stages of it.
Yeah.
Just to go
I
back
think we are going to,
for a second.
yeah, you mentioned about, go ahead, please.
He
Yeah.
was just mentioning about h bar, angular momentum of a photon, and the speed of light according to relativity. And these were connected somehow to the friction in the vacuum on large scales. And I'm just wondering, what was the connection, Wenzhong?
Okay. First, H Planck constant equals to equivalent mass m multiplied by light speed c, and multiplied by wavelength lambda.
Yeah.
Oh, if you do differentiate both sides of the equation against the time, so dH divided by dt equals to 0 because h is a constant, do not change with time.
Yes.
So one side of the equation is 0, another side is dm divided by dt multiplied by c lambda plus d lambda divided by dt multiplied by mc.
Right.
You can cancel out the c because c is a constant.
Yes.
So you arrive with the equation lambda divided by dt equals lambda divided by lambda divided by dt equals to minus m divided by dt.
Right. So this is all in your paper, isn't it?
Yeah, in my paper. Then in the end, if you assign that to equal to a constant, then actually you arrive the mass, equivalent mass of the photon change with time. So that's make me think the mass and the energy of the photon change with time. So there must be a friction to cause this. So then I use a damped, oscillating model. I derived the same thing, same equation.
Okay.
Then from that, I derive the relationship between the, the cosmic redshift and the Hubble constant. The relation between them.
Yes.
Yeah.
I remember reading that.
Yeah. So actually, I get the physical origin of the Hubble constant is a time constant. It's the the equivalent mass, the friction of the vacuum divided by twice of the equivalent mass of the photon.
Right. Okay.
So something like, yeah, like that. So it's a time constant.
Okay.
This can use two methods. One method is, from h equals mc lambda, you differentiate it with t, the time.
Yeah.
You can get this. And also from damped oscillating model, you can derive this as well. But you get more information about the Hubble constant. What's its physical origin and the physical meaning?
Right.
Yeah.
And this is from the paper, The Foundation of an Emerged Superphoton Theory?
Yeah.
Very good. So where you can figure all of that out just from those beginning things of differentiating the Planck constant over time and adding in the speed of light and the mass.
Yeah.
And the wavelength.
Yeah.
So, or sorry, what lambda was the wavelength?
Wavelength. Yeah.
Yeah. Okay. Cool. So that's it. Yeah. I mean, because I think I read part of this part of this paper where it's talking about photons. It's an interesting paper where it's talking about photons able to split into, like, it loses energy and these become super photons.
Yeah.
Right. What I was going to ask, because like super photons sounds like it's going to be massive, but by the sounds of it, these super photons are even smaller than normal photons.
Yeah.
And are they faster, or are they the same speed?
Yeah, because from the damped oscillating model, you can calculate the every cycle of the normal photon when it travels through the vacuum. Every photon they lose the same amount of energy. So from this simple model, you can derive every cycle of any photon, they lose the same energy. The energy equals to Planck constant multiplied the light speed.
Hang on a sec. Right.
Sorry. I am trying to connect something.
No problem.
Hold on.
You've got it. Okay, go ahead there.
Go ahead.
Yeah. It's a very. Let me think. No, I cannot remember clear. It's a. No, sorry, I made a mistake. It's a Hubble constant multiplied by Planck constant.
Yes. Okay, interesting.
Yeah.
They're not two things you hear together too often, I wouldn't say. So you're talking about, yeah, so you have the photon losing energy, and you describe it as a kind of advanced tired light theory, which is interesting, because I remember talk of tired light years ago.
Yeah.
And it's interesting. So it's the idea that if light travels like vast distances across space, does it lose energy? And I think they were suggesting that it did, but I don't think they ever actually found any experimental evidence of that, did they? Or maybe.
The cosmic redshift, you can measure the frequency and the wavelength of the photon. After that, they travel a long distance, the wavelengths become longer, the frequency becomes smaller. This is a cosmic redshift. This already being observed, but how to explain it?
Yes.
Yeah, the Big Bang, said it the space, expansion.
Yes.
To make it longer, the wavelength longer, the frequency shorter. But
yes.
The tail light said the light, when they traveling through the vast vacuum, they lose energy gradually.
Right. Yeah. So this all ties in and
my simple model can calculate. So every cycle, the photon lose a small amount of energy. Interesting thing is, whatever the photon, whatever frequency,
Yeah.
one cycle, they lose the same small amount of energy, Hubble constant multiplied by Planck constant.
Fascinating. I like the
Yeah.
way it's so neat.
Yeah, it's very small. It's 10 to minus 51. So very small amount of energy, but it has a very long, extremely long wavelength.
Right. That is very interesting.
Yeah.
So, because like some of the other theories was that maybe the light is leaking into a different dimension. It seems to me that you're basically looking at a theory of like light eroding. Is that kind of where?
Yeah. Light fatigue. Or yeah.
That's very
Yeah.
poetic or something.
Yeah.
So well done, Wenzhong. I really like your theory, and I think it has legs.
Yeah.
Yeah,
Yeah.
I like to see the paper. I am not. Can you?
I can post a link to it if you'd like. Yeah.
Okay.
Cool. And I could share it as well, but I can screen share it. Might help. But I'm going to post it in the chat. There you go.
Let me see.
I mean, there's probably no point in me screen sharing it, but if you have it, but here it is. I don't know if, yeah, you should be able to see that. So these are the equations you were talking about, DHT. Yeah. And so you have the speed of light. Yeah, I mean, I saw these, and it's great to have you explain it, though. It just goes in so much easier. There's a concept. And then, so this is Hubble and the Planck. There's a minus here, though.
Yeah, it's because the photon lose energy.
Oh, right. Okay.
To the vacuum. Yeah.
Okay. So are you saying that this happens at the same rate that we see the redshift occurring?
Yeah. In the end, I derive the the exponential relationship between the wavelength change.
Yes.
Yeah, and the distance it travel.
Yeah. Cool. So you're saying so you're thinking that the expansion theory, therefore, is unnecessary, correct?
Unnecessary, yeah. Absolutely unnecessary, yeah.
Yeah, of course. And then, so do you have a different? Do you think the Big Bang, therefore, is false completely, or?
Yeah, it is false completely, yeah.
That's interesting. So does that mean do you think the universe had a beginning, or?
I cannot make prediction for that.
Yeah.
But I know I work out the energy mass balance. They are all conserved. I know through my theory we can give a picture how the mass and energy they move around in circle in the universe.
Right. The mass. Yeah. Okay.
Yeah. Because the small amount of energy, Planck constant multiplied by Hubble constant is a very small amount of energy and a huge wavelength.
Yes.
So you are saying that Planck constant is changing?
Pardon?
Are you saying? See, you are saying in your equation 2, you are saying dH by dt means that the Planck constant is changing, or it's not changing? Okay.
Planck constant is not changing. It's a constant against the time.
Okay.
Cool.
And then the H, dm, how do you get the H? Or just a constant? Is just a constant? You are saying H is the capital H is a constant?
Yeah. It's a rough assumption here, but this kind of trick always used in physics. When you get this two sides equal, one side equals another side, then you can say, they may equal to a constant.
Oh, can you do that? I'm not sure. But,
yeah, that is a little bit uncertain, but later on, that's why I use another method, damped oscillating model.
Or you prove it?
Prove it, yeah.
Oh.
It's not absolutely constant from the damping oscillating model. Actually, it changes with the wavelength or frequency of the photon, but that can be ignored, neglected, because it's so small.
Oh.
Interesting.
Yeah, but actually the Hubble constant is, if you speak, very strictly accurate, it's not a constant. It change with the wavelength, but that change is quite small.
Oh, so the capital H is a Hubble constant?
Yeah.
Oh. How do you come?
Yeah. Sorry, go ahead there, Rajan.
Okay, how do you equate that? How do you equate the that's equation 3, right?
Yeah.
D lambda over lambda T. Let me switch off this. Okay. Oh, 1 second. All right. So you have the. Can you hear me now?
Yeah, I can hear.
Okay. So the equation 3 says
Yeah.
D lambda over lambda T equals minus Dm.
I go to get another, my mobile phone. I can see my paper. Otherwise, I cannot see my paper.
Okay.
Oh, okay.
Yeah, we'll wait for you.
Yeah.
Okay.
Oh, what I could do is share the paper. That might be good.
Oh yeah.
Okay, I'll try and do that.
Okay.
I would probably be better for Wenzhong to share it as well, because otherwise, he'll be able to scroll back and forth. Yeah, Wenzhong, you could probably share your screen even if you wanted to. But whatever whatever is easiest for you.
Yeah, maybe I share my
Yeah.
screen. I do not know how to use Team. I ask my wife come to help me.
Oh no, I can tell you. We should be able to tell you. So if you look, you have the icon for the video, and next to that the icon for the microphone, and then beside that is a box with an arrow pointing up. Do you see those?
Open share tree, yeah. Okay.
Share content, yeah, and then there should be like screen and then windows, and then if you click on the windows, it will give you all the windows that are open in the background. So, and then you can click on your
Okay. Okay.
This
Let's
see. You're sharing the journal. Well, make sure you're sharing what you want to share, and then you're sorted.
Fair Explorer. Let's see. Oh, where maybe.
We've kind of lost your video.
Oh, really?
Yeah. What's happening.
I do not know how to. Sorry, I do not know how to use it.
Right. Could you press the video button again?
Yeah.
And turn it on and off, maybe. You
yeah.
did. Oh. Yeah. Okay. We've lost your video, but.
Oh, I found this. Let's see.
The problem with this
yeah,
this whole software is that I can't tell if you're like given all the privileges and permissions that you need or not. Like there's no indication, you know. I can click it on and off and it works, but it doesn't tell you which condition.
Yeah, now I can see the paper now, equation 3, yeah.
Great. Okay, well, run through that then. I think Rajan was asking a question.
Yeah.
Yeah, this is a trick, you know, used in physics very frequently. If you know, for example, d lambda divided by lambda delta t equals to minus dm divided by m dt. So in physics, if you go to read, you know, the physics books, this, you know, being used quite frequently. You let it first equals to a constant, then you multiply it by dt, you get this equation 4. So its assumptions it equal to a constant, but this has been used quite frequently. I only can see this. You cannot 100% sure it's a constant, but it works. This trick works in many times in physics. So that's why later on I moved to a, you know, damped simple harmonic oscillating system with viscous resistance. So this
what I am used to is Hamiltonian. The H is Hamiltonian. The time evolution, I actually put it in our paper also. The time evolution comes very similar to what you have, the exponential function. That's the equation 5.
Equation 5, yeah.
So that time evolution comes from Hamiltonian. So H has to be Hamiltonian operator.
Right.
Yeah, I derived the equation 5 from equation 4. You are correct. Lots of the tiled light, you know, theory directly get equation 8 by assumption. Yeah.
But I am not sure about the if they have something constant. I would say it's a function. In that case, H has to be a function, not a constant. Then it's okay. But I have to look at it again. But the other derivative, the equation 5 seems to be quite normal. Again, but your interpretation is different. You are not interpreting as a Hamiltonian. So that's what I'm a little bit not sure about that.
But
those equations.
It's not a constant, no, Rajan? I thought it was a...
Yeah, that's what I think we have to prove that it's a constant.
Well, right. I think there's a debate over whether the Hubble constant is, but I think that's kind of irrelevant here, because it seems like, and this was the question I had for Wenzhong, is like, since you're using the Hubble constant, I mean, isn't that a measure of the expansion of the universe anyway? So doesn't it kind of presuppose the expansion of the universe by using it? Or do you know what I'm trying to ask, Wenzhong?
Yeah, you mean in the Big Bang they explain this as an expansion of the universe?
Exactly. Yeah.
You use the expansion of the universe, the space. You can directly the same equation as equation 4. That's correct.
Okay.
Yeah, but the problem with, you know, space equation, space expansion is energy, mass all become, you know, unconserved.
Right.
You know, that's the big problem with the space expansion.
For sure. Yeah.
Yeah, but I'm when I write this paper, I'm worried people maybe think, oh, the previously it's a assumption. Now you derived from a very simple h equals m multiplied by c by lambda, but how do you explain the constant, the Hubble constant, the capital H? You can explain it use tilde light. You can explain it use space expansion as well.
Yeah.
So that's why later on I use damped oscillating model to derive it again more accurately. If you look at equation 39,
Okay.
I think it's in page
Yes.
5226. Yeah.
Okay. Yeah, that looks interesting.
39. This is derived from the damped oscillating model. H actually is not a constant. It's you can approximate it to a constant.
Yeah.
Oh. You derive this H.
Yeah, the capital H is it's the Hubble constant.
Oh, okay.
Yeah, you can approximate it to the Whisker resistance coefficient Rm divided by 2m. M is the effective mass of the photon.
Right.
It's a time constant.
The constant with time. It doesn't change with time.
Yeah, it's from, let's see where it is. I explained it somewhere.
Oh.
F tau. Let's see.
Interesting.
Yeah.
Which equation is it, or which page?
Let's see.
Oh,
sorry, I didn't prepare well, so.
Oh, that's fine. Do you want me to scroll up or down? Or no, scroll down. Okay, so we've reached the end. It might be a different paper. Or it could be, yeah.
Yeah, here is
Oh, actually.
Yeah, here, just below the equation 39, I said the frequency and wavelength dependence terms in equation 39 are extremely weak because the extremely weak dependence has been observed experimentally. It cannot be explained by expanding universe or space theories. However, it is derived quantitatively above. I derived it. It has also been explained previously by a tilde light theory as well. Tilde light theory can explain 39. Whatever you think the mechanism may be, that paper I referenced, he used, he he used in the vacuum, there are some electrons. So photon react with electrons to lose energy. He derived similar equation like 39.
Right.
So, and got, observation evidence to support this as well.
Okay. Yeah, that's interesting. I see Aleksey's joined us as well.
Okay.
Oh, okay.
Hi, Aleksey.
Oh, welcome.
I'm here. Good
Hi.
evening.
How are
There.
you, Aleksey?
Morning here.
Rajan, yeah.
I thought the meeting will begin at 7:30 a.m. of my time because it was written me 12:30 a.m. of the general time.
Oh,
And
Greenwich Mean Time would be like right now. Greenwich Mean Time is around 9:30. But here you're not late. Well, we did start at 8:30, but it doesn't. Oh, did I? Yeah. I think I said to you 8:30 p.m. But that's because we moved it forward because we thought it was around 3 a.m. where you are, but it's actually around 6, is it? So perhaps moving it forward wasn't a good idea. We could always move it back if it suits everyone.
I'm lucky that I checked. I thought maybe it will be at usual time, and I see that probably the meeting lasts already for several hours, isn't
Right. Yeah, we've been on.
too late?
We started at 8:30 my time, Greenwich Mean Time, which is probably about 6:30 your time, is it?
My time now 3:30 a.m.
Oh, 3:30. Right. Yeah.
a.m. Yes, it's morning. It's early morning. I'm early bird.
Great. With 3:30, yeah, that's fairly early. Like that's like the middle of the night. So basically, we started 2:30 your time. We moved it forward to so that it would be a little bit earlier for you, not so dead of night, you know.
Mm-hmm.
So
okay. I see the paper by Wenzhong, isn't Wenzhong Zhang?
Yeah.
This
hi.
Yeah. Hi.
That's
Hi.
right. You can see that.
How are you?
Great.
Yeah.
Yeah.
Yeah, we were wondering where you are. Maybe the time got mixed up or something.
That's it. It seems like it. I think it's all sorted now, though. If you tune in to 2:30 is your time is 8:30 my time, Greenwich Mean Time. I think Universal Time and Greenwich Mean Time are equivalent, aren't they? Or are they?
Is it?
I'd have to look that up actually. Maybe that might have been my error. Maybe I equated Greenwich Mean Time with Universal Time. I mean, it seems like Greenwich Mean Time would be Universal Time because it is
There's international dateline and all that, but
yeah, you'd think it would be, but maybe it isn't. So, okay, I had one other question about not so much tired light theory, but the fact that the photon is losing energy is it doesn't put a life a kind of a sell-by date on the universe, does it? I mean, wouldn't the particles eventually run out of energy and the universe just winds down, grinds to a halt, or is that a problem, Wenzhong?
No, because this small amount of energy have a wavelength, same size as our observed universe. So in my second paper published, I use some quantum theory.
Yeah.
to conclude, this small amount of energy, this small particle, they will produce a kind of, Einstein, both Einstein condensation.
A post-Einstein.
It's kind of in low temperature. The helium will produce the Einstein both Einstein both condensation.
Yes.
Yeah, you know that idea.
Yeah, I do.
So the very small energy and long wavelength photons, they will produce a kind of quantum liquid.
Right.
Quantum liquid as Einstein both condensation.
And that will be the end of the universe.
No, that is not the end of universe. That is something behavior different with our normal photon. Because they have huge number, they have huge wavelength, they will spread out into the whole universe evenly.
Yes.
So when for example, the sun emit photons, energy and mass out, this kind of Einstein both condensation quantum liquid will fill up. So it produces circulation.
I see. So you're saying that this is an energy reservoir that turns into matter, and then the matter turns into this energy, and it's like a cycle.
Yeah, correct. You are correct. This liquid in the for example, in the sun, because there are some internal reactions, let this liquid become gas. The normal photon, we can see it like gas.
Yes.
It flow out. But because when it flow out, it's a opposite direction, like the quantum liquid. The quantum liquid try to fill up inside the sun, but the normal photon shooting out. So they have a friction, and also between them they have a force as well. The friction force to the normal photon actually is the driving force to the super photon to drive them to fill into the sun.
Yeah. So I think, yeah. Go ahead.
That is two floods of different photons. They achieve a mass and energy equivalent energy, conservation.
Right. So you're saying that the energy and the mass, these two photons somehow work to convert energy and mass? Or did I understand that correctly? Or just
yeah. In my theory, every photon they have a mass.
Yeah. Oh, really?
Yeah, they have mass. They have energy.
Okay, because usually photons are meant to be massless. Yeah.
That is.
I know. Sorry, I know several evaluations of the photon mass. It is about 10 power minus 40 kilogram.
Is this the rest mass?
By Wenzhong, it is relatively this mass. In Russia, there are also evaluation even 10 power minus 44.
Right.
I have observed such result. And by Wenzhong, it is 10 power minus 40, isn't?
No.
A photon.
Yeah, the mass I'm talking about in my paper, actually they are equivalent mass.
Equivalent mass.
Yeah, they are not a rest mass, what Einstein talk about. It's something like energy equivalent mass.
Right, I understand. So
Yeah, Einstein has said that a solid represent an energy inside. It is if we take a solid, it contains a lot of energy inside. A solid represents an energy. It's possible to understand his words by this way.
that's true.
Yeah.
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 Go ahead there, Wenzhong.
I didn't get into Einstein's rest mass because that is a concept troubles me, because you must rest against the reference frame. Is it correct? But what reference frame do you use to get a rest mass for photon?
Yeah, good question. Because there is no absolute rest mass, or there's no absolute frame, is there?
Yeah. So I think that is it's something I couldn't fully understand. So I use energy equivalent mass.
Well, that makes sense, doesn't it? Because I mean, in Einstein's equations, he's talking about energy and mass being equivalent, right?
Yeah.
So if you have if you figure out the energy of the photon, then you know its mass.
Yeah.
But isn't that a contradiction of like the whole kind of other points in relativity, that once you have mass, then you cannot travel at the speed of light, or do you see a way around that? Or
yeah, in my paper published in the October issue, the first paper, I explained that.
Okay, I'll have to check.
Yeah, very clearly. If you have friction force in vacuum, and also because the photon lose a little bit energy, so the lost energy just be able to combat the friction force to keep it run at a constant speed.
Okay, I understand. So going back to the Bose-Einstein condensate, that sounded, you saying that's like a liquid, and then you have the photons are like almost like a gas, you were saying? Was it like an evaporation of the condensate? Did I understand?
Yeah. The normal photon actually is similar like a evaporation of the liquid photon.
Fascinating. That's really I like that. Again, I wouldn't call it poetic, but it's very evocative. Could be like
but is it like a superfluid?
Yeah.
Superfluid?
Yeah, superfluid. Yeah, you are correct. In the two-phase flow. There are two-phase flow. Mm-hmm. Yeah, one phase is the very small energy, long wavelength photons. They try to spread out in the universe evenly everywhere. So but in some hot spot, they try to evaporate them to shooting out them, like something like what's it called? It's ballistic propagation.
Ballistic.
Yeah, like that.
That's great. So are these wavelengths the size of the universe? You're saying the big.
Yeah, the super photons wavelength is equivalent to the size of the observer, universe.
Wow, that's pretty cool as well. That's a fascinating idea. So then am I right, correct in sort of summarizing that you think the universe is eternal?
Yeah.
Yeah.
Yeah, but there are fluctuations because there are dissipation. There's fluctuations. So there is a theory called dissipation fluctuation theorem.
Could you say that again?
Fluctuation dissipation theorem.
Hang on a sec, Rajan. Could you stop messing around with microphones there for 1 minute?
Yeah, the internet is coming on and off, so I'm trying to choose which one is the better one. So,
okay, we're just getting a bit of feedback. I think what you had at the start was like really good, but
how about now?
yeah, that's good.
Okay.
Okay, and Wenzhong, I didn't. It was something about flux. I didn't quite catch it. Am I getting that right? Flux?
It's you know, it's Raja just said it's superfluid, yeah.
Ah, superfluid, yeah, because
yeah, superfluid, yeah.
It's like the you know, like has zero viscosity and zero friction, or what is it, Aleksey? You've worked a lot with that, haven't you? Superconducting.
Yeah, actually,
Yes, I worked at the Exeter University in England in one team by Professor White and with Charles Williams, experimentally with the well-known superfluid. It is helium-4
Yes.
at low temperatures below 100 millikelvin. And it is very interesting liquid in some Russian in the Soviet Union. Some Russian teams believed that the superfluid helium represent a solid at the condition of superfluidity. It is possible to treat this liquid as a solid. There is such opinion. There are many opinions how to treat it, and also it is very interesting thing that this superfluid helium does not flow on some surfaces. For example, probably cerium. If you put this superfluid on cerium surface, it will not flow. You will see some areas of this, some drops. Not, it will not no go. Some drops will be formed on the surface of some solids, and there is no superfluidity properties on such solids. At low temperatures. It is very interesting fact. Maybe I have discussed this fact with Professor Pedro Contreras from Venezuela.
Okay.
His interest is in superconductivity, unconventional superconductivity, and Landau has said that the phenomenon of the superfluidity is akin to the phenomenon of the superconductivity, and
Of course.
in many ways.
I can
In many
understand.
ways.
but
And,
I think the magnetic and the electric properties are interactive. You know, that superconductivity is very closely connected with that.
Magnetic properties.
Yes.
Could well be. So helium-4 is like is considered a boson, is it?
Yeah.
How is that possible? Is it to do with the number of electrons it has or something? It's no longer a spin 1/2 scenario. I suppose. I mean, a proton is what? It's spin 1/2. So yeah, I'd have to look that up a bit more. I'm not that well up on superconductivity, but you were talking the last week about solids and gases that behave a bit like a vacuum. And if you think about it, a superconducting material just allows like electrons and photons to move through it, kind of like an ideal gas. So it's like the object isn't there. So in a sense, is that correct? Have you heard of this?
For example, it was said that there is to treat superfluid helium-4 as absolutely a black body.
Oh, cool.
Absolute black body, and as a vacuum as well.
Do you know what gives it that property, helium-4? Is it the structure of it or something?
Structure. It has a complicated structure.
Okay.
Below the so-called lambda point, 2.18 Kelvin, probably, if you remember.
Yeah.
If I'm right.
This is a very, very interesting point. So even superfluid helium-4 is an ideal black body radiator.
It can be treated by somebody. It is said there are many assumptions, many directions how to treat this liquid, and somebody says that it is ultra cold but usual liquid, but superfluid, and somebody treats this superfluid as a solid below this lambda point. You see that below this lambda point, the superfluid helium-4 has already 3 branches, and Landau has put these 3 branches one consequently, one near the other, consequently, from the left to the right, but not from the bottom to above each other. Because before Landau, these 3 branches of the liquid helium-4 initially were put like for a solid, one above another. These 3 branches below the lambda point, and both are right. Moreover, I say that Landau was more right to put these 3 branches one after another from the left to right. And what we see, Landau has said that these 3 branches are called the phonon branch, the negative photon branch, and the positive photon branch, because you see that there is a maximum maxon like a particle, and there is a minimum roton like a particle. There are 2 particles. The first particle, maxon, looks like antiparticle, and roton looks like a particle. And you see it is this structure like a solid particle and antiparticle. For example, an electron and positively charged ion. And this roton branch, I'm not agree with Landau. It is too hard to explain. I have to spend a lot of time to explain my opinion, my theory. Simply, it is unknown that it is known that helium-3 has the Cooper pairing phenomenon. You know the Cooper pairing phenomenon, Bardeen-Cooper Schiffer. They have received a Nobel price a long time ago. And this the Cooper pairing phenomenon there is only was found only in the liquid helium-3, but not in the liquid helium-4. And my opinion there is that the positive proton branch of the liquid helium-4 in this branch there is also the Cooper pairing phenomenon, because you have to know that I studied at the Exeter University the evaporation, quantum evaporation process. They have developed this method. Professor White, who is academician because he is a member of the Royal British Society. It is means that he is an academician for Russia, for Russian academic system. He's an academician because he's a member of the Royal Society of United Kingdom.
Yeah.
And he has his team has developed this method called the quantum evaporation system, and they use a heater below the liquid surface. They have they study the purified, very poor purified liquid helium-4 below 100 millikelvin. You have to know that below 100 millikelvin, the liquid helium-4 has already the same propagation velocity. If you have temperatures below 100 millikelvin, for example, 50 millikelvin, 10 millikelvin, the velocity of propagation is the same. If it is above 100 millikelvin, you have to find out that the velocity is changed with temperature. With increasing temperature to up to the lambda point 2.17, 2.18 Kelvin. And they have developed this method of, it is called the quantum evaporation method, and it is very powerful method. And I have found that in the third branch, that is called the positive proton branch by Landau, there is the Cooper pairing phenomenon, namely due to it was found due to this quantum evaporation process, because bulk elementary excitations generated by a heater inside the liquid, they propagate from the heater to the surface between the helium-4 and a vacuum. And at the surface, there is evaporation of helium atoms inside a vacuum from the liquid. And in order to evaporate one helium atom, we need to have energy equivalent to 2 bulk elementary excitations. This means that 2 bulk elementary excitations, that is the Cooper pairing phenomenon, can evaporate one atom. This quantum evaporation process manifests that there is the Cooper pairing phenomenon in the liquid helium-4, in addition to the liquid helium-3. And this is my opinion, this is my work, and I have to say it. I say that nobody focused on it, and nobody focuses on the fact that the liquid helium flow does not show its superfluid properties on some surfaces, for example, on surface of cerium, and this fact is also ignored. I don't know why. And you have to know that there is the Cooper-Parham phenomenon for the third branch, namely for the positive proton branch of the liquid helium-4 at low temperatures, below 100 millikelvin. Because below 100 millikelvin, there is already the same propagation velocity. It does not change. We can see any significant change of the propagation velocity in the superfluid. And also, if you look at my work concerning the liquid helium-4, the second branch called the negative proton branch is also interesting. And I think that it is possible to treat an atom, for example, a helium atom, single helium atom propagating in a vacuum. This atom, any atom, it exists in four spaces simultaneously, in four spaces, in positive real space, in negative real space, in positive imaginary space, and in negative imaginary space. It is anywhere, right away. So this gives for an atom in a vacuum to interact with anything. It is easy to interact for a free atom. And I think that this the second branch called the negative proton branch should be it is better to put it to negative to have negative energies, not positive energies. And it is better also to put it it is hard to say. It is better to demonstrate on a figure. You have to know that Landau put these three branch, the phonon branch, the negative proton branch, and the positive proton branch, they go one from another. They represent a continuation. For example, the positive, the phonon branch, the end of the phonon branch is coupled with the beginning of the negative proton branch by Landau. And the end of the negative proton branch is the beginning, is coupled at the beginning of the positive proton branch, the third branch. And I think that this second branch called the negative proton branch should be positioned like a mirror. If you put a mirror in the plane of the x-axis, yeah, this will reflect this branch, the second branch, to the negative energy,
Aleksey, I have a question. Is a negative photon is like a dark photon?
It is called about bulk elementary excitations in the superfluid helium-4. And if you show me branches of the photon superfluid, like branches of the liquid helium-4, and if there is a maximum or and the return minimum, like something like this, for the photon superfluid in a vacuum, it is possible to have an analogy, but I'm talking now about the superfluid helium, three branches of this.
Aleksey, you're saying roton, not photon. Is that what you're saying? Yes, roton.
Yes, negative proton, yes. Negative proton branch and positive proton branch. And there is only one phonon branch.
Yeah.
By Landau, the roton branch. There are two roton branches and one phonon branch. Landau has called the phonon branch because the wavelengths of this branch are very large, very large. It is wave numbers approaches 0 for the phonon branch. It is hard to understand, but if you put these three branch one above another, you will have the wave number approaching to 0 for all these three branches. It was done before Landau. So my calculations is based on this assumption that at the roton minimum, at the maxon maximum, you can use the wave number approaching to 0. This is the boundary. This is the boundary. You see that all three branches have two boundaries. And at both boundaries, you can treat it as the wave number is going to 0. This means that wavelength is going to an infinity. But this is the problem because in each branch there are different particles. You see, Landau has said phonon branch, negative roton branch, and positive roton branch. And I associate this roton minimum already with electrons which are inside the nucleus of helium. If phonon branch, it is possible to see that it is coupled with electrons outside the nucleus of helium atoms. Negative roton branch and positive roton branch, this is my opinion, already give this picture. It's already particles coupled with electrons inside the nucleus of a helium atom, because you see that a helium atom consists of two protons and two neutrons, but one neutron consists of one electron and one proton. And the position of neutron in a helium atom is defined by a position of electron. And you see that there are two electrons in the core of helium atoms. There are two electrons.
Yeah, so that's the way it's behaving.
Because there are two neutrons which contain these two electrons, and these two electrons are coupled with each other. You can't act to one electron without some response from the other electron. They're coupled because you can't to reach these two electrons too close to each other. They will repel, for example, because they're electrons. And if you put some action to one electron, the second electron will behave according to the motion of the first electron. You act on it. And this means these two electrons are coupled. And yeah, and the position of these two electrons gives the positions of neutrons in the core. If you act on an electron in the core, it will rotate. They will rotate as a couple, and therefore you will see that
like these two. Aleksey, can you see that?
yes, I see, and
These two, two inside the core, or would that not make 4 electrons? Or sorry, am I misunderstanding? I go back to
helium-4. You see, yeah, this picture, the upper left picture, helium-4. Yes, this one. Yes, you see that two blue looks like neutrons, and two red looks like two protons, isn't?
yeah.
Two and around this helium-4.
Yeah, I follow that.
It is a good picture, and the phonon branch, because you use heat inside the helium liquid, the superfluid helium liquid. You use heater to excite bulk elementary excitations, and in the phonon branch, the heater heats. You see that in the helium, in the superfluid helium-4, we deal with thermal phonon, thermal elementary excitations, the thermal particles. Therefore, you heat a heater inside the superfluid helium-4, and you have bulk elementary excitation that propagate from the heater to, for example, to a bolometer, if a bolometer is situated below the liquid surface, or if there is no bolometer, the bulk elementary excitations are propagating up to the surface of the superfluid and evaporate some helium atoms. Only two-proton branch can evaporate helium atoms. In the negative proton branch, there is one bulk elementary to one helium atom process. But in the positive proton branch, we need two bulk elementary particles, that is a Cooper pairing phenomenon, to evaporate one helium atom.
And the negative photon due to antiparticles like positrons.
Photon?
Yeah, negative photon is associated with the positron, the antiparticle of electron.
I'm talking about helium atoms, but not photons.
Okay.
It is about helium atoms. Atoms are more probably more complicated structure, because a helium atom consists of two protons, two neutrons, and
Yes.
two electrons around this core. And you see that one neutron consists of also one proton and one electron. Is it okay?
Yeah, I think I understand it. Yeah, go ahead.
What you are talking about is a negative photon. I wonder how it comes about.
Who shows these pictures?
I just played that video just to give some people an idea of what we're talking about.
Okay.
That was me.
Superfluids.
Yeah,
Yes.
that's kind of what we're on, isn't it?
The mechanism of the superfluidity looks like if you have some mass propagation in one direction, in the opposite direction you can have energy propagation. As a result, you can see that the superfluid flows in one direction, but heat flows to the opposite direction. You see atoms, helium atoms flow from one vessel to another. If you have two adjacent vessels.
Yeah.
But energy can flow by because not only atoms are coupled, can be coupled with electrons. It is a very complicated structure, but also nucleus of helium atoms can be coupled.
Oh, okay, that's interesting.
Not only atoms, but also nucleus.
Well, that would make sense, wouldn't it? I mean, the nucleus is kind of smaller, isn't it? So it's if an atom could be coupled, then surely a nucleus could be. It seems logical, anyway. I was thinking, you know, this idea of like that Wenzhong had about that space is essentially a superfluid.
Yes, it's a vacuum. The superfluid helium is treated as a vacuum.
Yeah, you were saying, is this part of what
you have to know that in a vacuum, not in superfluid helium, in a vacuum, you can see that one photon with some certain energy can annihilate this creation of one pair consisting of electron and positron.
Yeah.
And therefore, annihilation of electron and positron give one photon with some. And it is treated also that a vacuum represent some cells consisting of pairs of electron and positrons. There is such theory, it is said that a vacuum represents crystals consisting of electrons and positrons coupled together. And if you have a photon with certain energy, it is very high energy, you can see that from nothing, from a vacuum, one electron and one positron are created.
Yeah, actually, Aleksey knows our paper.
Sorry,
I don't think he's read it yet.
Okay.
Yeah, Aleksey, I'm now thinking about this same way as you as well. Try to understand the vacuum. Yeah.
Yeah, it's very interesting. There's a guy that works with Rajan. He's actually worked on the paper that we wrote called Manuel Malaver, and he works with another group whose name I forget, but I'll send you on their details. And they're a group of physicists, and they're fascinated by the idea that of explaining gravity in terms of fluid mechanics. So, you know, just I guess it's like general fluid mechanics from a like. That looks backwards actually, but to me anyway. From an engineering point of view, I assume they're just applying that to kind of, you know, space time, which is interesting because you have this idea of like gravity is not a pull mechanism in relativity; it's kind of like a push, but certainly a flow of some kind. So, I mean, I'm not sure it might be a worthwhile thing, but it just reminds me of what you guys are talking about, like a super.